All righty. Let's get it done. All right, so we're going to be talking today, finishing up our notes on chemical bonding. We're talking about intermolecular forces. So these are the forces that are between molecules. So like what holds a water molecule to a water molecule. You'll see them often written as IMFs. And these affect physical properties. Like what temperature something melts at, or what state it is at room temperature. So we're going to talk about 3 different kinds, and they vary in strength, but all of them are weaker than the bonds that hold an atom together. So we did the little chart, and that's when we were comparing covalent, ionic, and metallic. All 3 of those are stronger than any kind of IMF that we talk about today. So the strongest intermolecular forces are going to exist between polar molecules. And remember, polar molecules have a positive and a negative side. I put them in parentheses because it's not a whole positive or a whole negative charge. It's a partial positive or a partial negative side. And that's due to the unequal sharing of electrons. They're pulled more to the electronegative atom, and then so they're not shared evenly in a polar molecule. And for IMF, like I said, we're just covering the big picture over them. If you take AP chemistry or you take chemistry in college, they'll go a lot more in depth about these different things that we're talking about today. So the first one we're going to talk about is the dipole force. And that's when the positive end of one dipole is attracted to the negative end of an adjacent or neighboring molecule. And dipoles are equal but opposite charges that are separated by a short distance. And like I talked about, they're caused by the unequal sharing of electrons. And this dipole, this is medium or middle, not medium, middle. Or however you want to put it, second strongest. It falls in the middle. So middle, strongest, not proper English there at all. So we've talked about HCl. We're going to find out that that's hydrochloric acid, but that's a covalent compound. Chlorine's a lot more electronegative. So the electrons that are shared here get pulled toward the chlorine. And then it has a negative dipole, and the hydrogen has a positive dipole. And those are, I think they're called sigmas. That just shows it's not a full positive charge or a full negative charge. Some kind of Greek letter. So this is just showing you a couple of hydrochloric acid molecules. So this is the covalent bond. That is an intramolecular bond. And this is the dipole force, which is an intermolecular force. It's not a bond. the things that we're talking about today, even though one of them is called hydrogen bond, it's not really a bond. I didn't do attendance, I just remembered. So it's holding this hydrogen chloric acid molecule to this hydrochloric acid molecule. And this is the negative dipole, like I said, because of the uneven sharing of electrons, and this is the positive dipole. So hydrochloric acid is a polar molecule. And then they'll line up, opposites attract, so they'll line up, so they'll be like that, opposite, negative to positive, negative to positive. All right, I'm gonna go and do my attendance before I forget. All right. Sorry, y'all. Already did this one today. This one, something. I do, y'all. I know we're fifth period now. All right. Whew. Sorry about that. All right, so our next one is hydrogen bonding. And I know y'all have heard of that before because of biology and water. So even though we call it bonding, it's not really a bond, it's a force. It's going to be the strongest intermolecular force. So a hydrogen atom that is bonded to a highly electronegative atom is attracted to the lone pairs of that electronegative atom on an adjacent or nearby molecule. So it's what gives water such a high boiling point, because the water molecules are held together pretty tightly. So it takes a lot of energy to move them apart and make it go from a liquid then into a gas. Only 3 elements do this: nitrogen, oxygen, and hydrogen. Nitrogen, oxygen, and fluorine, sorry. So obviously it's hydrogen bonding, so you have to have hydrogen present, but hydrogen with something that contains nitrogen, oxygen, or fluorine is possible. And if you like a mnemonic to help you remember that, no orange friends. Those are the 3 elements that can have hydrogen bonding. So this would be an example of that. I know y'all done this before with water. Once again, the hydrogen bonds is the intermolecular, is holding a water molecule to a water molecule. The covalent bonds would be what's holding the hydrogens to the oxygens. But this hydrogen is slightly positive because of the unequal sharing of the electrons. So it's going to be attracted to these negative electrons on that adjacent atom. And once again, that could only be oxygen, nitrogen, or fluorine. So this would have to be nitrogen or fluorine for that to be able to happen. No other element would that occur, those elements would that occur with. So that's our strongest one, and that's why water has some of the properties that it does have. All right, and then our last one, our weakest one, is called the London dispersion forces, or sometimes you'll see it as LDFs. And this one results from the constant motion of the electrons and the creation of an instantaneous dipole. So not a dipole that stays, but the electrons in the electron cloud just shift for some reason. So just for a moment, there's a positive and negative side, but then that'll change again. All molecules have this, but only ones that can use this type only are your non-polar molecules. So in other words, water has hydrogen bonding, but it also has London dispersion forces. So every kind of molecule, remember when we're talking about this, these are all molecules, so they're all covalent compounds. All of them can have an LDF, but then many of them also have something stronger that goes along with that LDF. And this is kind of drawing of that. You don't need to draw this at all, but you'll see with this one, we'll have maybe for some reason, the electrons shift and you'll have like maybe just a negative side, and then they may shift again. And then that negative side may switch to the other side. But because of that, that attraction will happen and then it'll be gone, and happen and then it'll be gone. All right, I said early on that intermolecular forces affect the properties, many of the physical properties of compounds. So this kind of is what we're looking at here. Gases, an example of a gas would be CO2. And CO2 only has dipole, no, it doesn't. It has LDF, sorry, it has the weakest ones. And that's the only kind it has is LDF forces. So most of these things we've been over already. The thing that is new to you would be the very last statement on each thing. So we know that gases have a low density, they expand, they fill a container, but gases also have the weakest intermolecular forces. So not all gases have an LDF only. Some of them can also have a dipole-dipole, but this particular one does. So that means if they have a weak intermolecular force, that's what allows the molecules to spread out so much. Liquids kind of fall in the middle. An example of some different liquids would be fluorocarbons, compounds that are made of carbon and fluorine. And those are liquid at room temperature. These happen to have dipole. Dipole would be the type they have. So liquids kind of have, as far as talking about the intermolecular forces in the middle, they're intermediate. And then solids, example of that would be glucose. C6H12O6. And solids have the strongest intermolecular forces. So they hold the particles pretty close together, and that's why they end up being a solid. So molecules that exist as solids at room temperature, which today is very cold in this school, at room temperature have the strongest, or have strong intermolecular forces. That doesn't mean they all have to have hydrogen bonding. But if you're given a gas and a liquid and a solid, you should be able to know that the solid has the strongest intermolecular force. If you go down group 17, our halogens, they start as a gas. So those have the weakest intermolecular forces. And then as you come down to iodine and antimony, those exist as solids at room temperature. So their intermolecular forces are stronger. So we're going to talk about some other intermolecular forces that you may or may not be familiar with that are affected by properties that are affected by IMF. One is viscosity, kind of how thick something is. Water is not very viscous, but something syrup that's very viscous, it's thick, it's harder for it to flow. So as I increase my viscosity, it increases the IMF, whatever compound we're looking at. Melting point and boiling point, I kind of talked about those a little bit. Both of those are dependent upon the strength of the intermolecular forces. So the stronger that IMF, the higher the melting point and the higher the boiling point. So once again, if you had a list of compounds and I gave you all of their boiling points and I asked you which one had the strongest IMF, it would be whichever one had the highest temperature, highest boiling point temperature. Vapor pressure is also dependent upon the intermolecular forces, and vapor pressure is the tendency of a substance to change into a gas or to evaporate. So like fingernail polish, it has a lower vapor pressure. I'm sorry, it has a higher vapor pressure than water does. It will evaporate quickly. So the stronger the intermolecular forces, the lower the vapor pressure at a given temperature. So volatile liquids like gasoline, which vaporizes easily, especially if it's like outside, the temperature is affected by it, are held together with weak forces. So once again, if I gave you a bunch of vapor pressures, you should be able to apply that and pick out the one that has the strongest IMF or the weakest IMF. So a question like that may look similar to this one. So on these, you're going to arrange the following in order from the one that will vaporize more quickly at room temperature. So the one that's going to vaporize more quickly is going to be the one with the weakest IMF. So I'm going to want to start with the weakest IMF, and I'm going to want to go to the strongest IMF. So acetone and alcohol, right there, I would not expect you to know that that was nonpolar or that this one was polar. I would give you that information. Is water polar or nonpolar? Polar. It is polar. I would expect you to know that. Same thing. I would not expect you to know that acetone or hydrogen or alcohol, whether they do or don't have hydrogen bonding, but I would expect you to know that water has hydrogen bonding. So there you have some information. We only have one that has hydrogen bonding. So which one is going to evaporate the least quickly at room temperature? Which one? If the one that evaporates the most quickly has the weakest IMF, the one that evaporates the least quickly is going to have the strongest IMF. So of those three, which one has the strongest IMF? Our water, right? Because we said hydrogen bonding is the strongest IMF, and that's the only one of those three that has it. So water should be my one that is listed last. Strong IMF, it takes a long time for it to evaporate. So I got rid of that one. So now I have these two. I have one that is polar and one that is nonpolar. So look back over your notes. And if you look right at the beginning of your notes under B, 3 types of intermolecular forces. Before we even start listing them as 1, 2, 3, we said the strongest intermolecular forces exist between what kind of molecules? Polar. So which one should be in the middle? Alcohol. And that means that my acetone, which is nonpolar. That means all it can have is LDF because it is nonpolar. Alcohol would have LDF and dipole. Water would have LDF and hydrogen bonding. So once again, kind of given something like that, you should be able to kind of apply it. All right, there's no separate practice on those notes. You'll just see it on the test. So if you'll get out, or if you haven't already gotten out your, let's see, start my stuff here. Your practice. Like this, your VESPER practice. That would be one thing you could work on for the rest of the period. You also had the other one that was, I started off as a covalent bonding and it had the different names of them written off to the side. So you can work on either one of those. Once again, you're not going to be able to use this tomorrow. So you'll have to be able to know areas of electron domain. And remember, all you have to know is the molecular shape. Those last four, you don't have to know anything about the last four columns. And also just a reminder, because I know it's been a while, we are always concerned about what's going on around the central atom. Okay, so like for instance, let's just look at number 4. Si is my central atom. And it has 2 bonds, so it has 2 electrodomain areas. The fact that this sulfur has some lone pairs, that doesn't matter because it's not in the middle. I'm concerned about what's going on in your central atom. Because that was kind of some of the questions that have come about from my last 2 periods that I had before y'all. So to be able to do VESPER, you're going to have to be able to draw the Lewis dot structure first, because that's kind of the only way you can get to it. All right, so y'all got a little time to maybe about 10 minutes or so to work on that. If you have any passes left, yes, ma'am.